and watch it hit the target.
We have given ourselves 6 opportunities to make a trajectory correction maneuver. And each of those correction maneuvers uses the thrusters on the spacecraft to give a little push to the spacecraft to correct its trajectory.
One of the things that makes landing on another planet so difficult is that we're essentially trying to hit a moving target. The spacecraft left a planet that was spinning around the sun at its own speed, and we're now aiming for another planet. And we can't just aim for where the planet is at the time that we launch, but we have to aim for where we think the planet's going to be by the time that we get there.
All of those motions, the navigation team has to carefully track and predict where things are going to be in the solar system in order for us to successfully navigate to Mars.
The trip from here to Mars is over 8.5 months, and we need to make sure that we monitor all the sensitive instruments, science and engineering, to make sure that over the 8.5-month journey, everything is working properly.
The better we do our jobs during the cruise phase of the mission, the better the entry, descent, and landing phase of the mission will go, as well as the surface phase.
Kick it.
This robotics basketball is more mental in that you have to plan ahead, you have to design the robot. It's more innovative rather than reactionary.
You know, every year's a challenge. We always have to come up with a different design. This year we spent about a week just designing.
We get a lot of ideas, but there is also a lot of spirited debate. And I guess eventually we either vote or just come to a consensus, and that's how we make our decisions.
I learned a lot of technical skills, like how to program in C++.
Basically, I already wanted to go into engineering, so I just learned so much about robotics and so many of the mechanics about it.
I learned how to communicate, I learned how to build a robot, learned how to problem solve and get things done really quickly.
Everything I know about programming, electronics, it's all come from being on a first team.
In daylight, our big blue marble is all land, oceans, and clouds. But the night is electric. Seen from space, our planet comes alive with light. This new view of the Earth's night lights is a composite of data acquired by the polar orbiting Suomi NPP satellite. Aboard the satellite, a newly designed instrument called VIIRS is able to collect what scientists say is a remarkably detailed view of the Earth at night. In some places, city lights resemble solitary stars in the night sky. In other places, dense clusters of galaxies. The satellite can even distinguish brightly lit boats that line Egypt's Nile River, and the massive flames from gas flares produced as a byproduct of oil and gas exploration in the Middle East. As the satellite passes over the darkness of the Himalayas, it shows how human settlement is bound by natural borders. Even political borders are starkly visible in this view of North and South Korea, and in a line of fishing boats that dot the Yellow Sea. But not all light is electric. Glowing just as bright, flaming wildfires burn across Australia. This new view of the Earth at night offers a unique perspective for exploring the many places in which we live and seeing the impact of human populations around the world, no matter how faint or how bright their lights shine.
Hi, I'm Chris White, System Engineer leading the Integrated Sample Chain Test Program, and I'm here with your Curiosity Update. Today I'm standing in the MSL Vehicle System Test Bed with a test model of Curiosity rover, and we're about to do a scooping and sample drop-off test. So in today's test, we'll bring the scoop on the end of the arm down into this tray of specially prepared sample. We'll be taking images and identifying the target where we want to actually scoop. Then we'll move the arm over, open up the scoop. We'll scoop a sample of material. We'll close the scoop. We'll bring the arm back up to the front of the rover, and we'll drop a very small portion onto the observation tray. Then we'll spin the turret around and take additional images of the portion on the sample tray. Once we've acquired those images, we'll bring the turret around again and drop off a portion into the inlet covers on the top of the rover. The sample we need is not very big at all. In fact, it's about the size of this aspirin I'm holding. Once that portion is dropped in, it will go into the science instrument SAM. And when we're done with that, we'll bring the arm back out and we'll clean everything out. We have automatic cleaning functions that we do to clean everything out, ready for the next sample. This has been your Curiosity Update.
I'm Scott Maxwell. I'm a Mars rover driver, and this is your Curiosity Update. Through careful targeting, we've been able to shrink the landing ellipse for Curiosity, and we've been able to move it closer to where we want to actually land. In case we land in dunes that are like this on Mars, near the landing site, we want to be sure that the real rover is able to navigate around successfully in those dunes and get from the point where we landed to the point where we really want to be. So we've come out here today with the Curiosity Scarecrow rover, which is the same weight on Earth as the real rover is on Mars, to practice driving it around in the nearest thing to those dunes on Mars that we're going to find here on Earth. This is similar material and similar slopes to the dunes that we're going to find in Mars. So being able to test this rover in these dunes gives us a good idea about what the performance of the real rover is going to be in the dunes that we might land in on Mars.
Still making progress.
Performance on this rover is actually fairly similar to Spirit and Opportunity. A little bit better. We can climb in soft sand up to about 15 degrees or so, which is a little better than Spirit and Opportunity will do. We are in fact right now maneuvering it from an area of about 15 degrees of tilt to an area of about 25 degrees of tilt to try to explore where that break is in its performance. Our top speed is very slow, but our acceleration of that top speed is pretty much instantaneous. So we go from a dead stop to right about as fast as we're going to go pretty quickly. And it's really fun to, like, every once in a while, kind of leave the office environment behind and come out to an environment like this and see what the real rovers are going to be doing on Mars. It kind of connects you to it and reminds you that, that the computer models that we play in are a far cry from reality. This is that reality. I'm Scott Maxwell, and this has been your Curiosity Update.